In Chapter 5, Section 5, we will look at substitution rule, one of the more powerful rules for taking integrals, and these can oftentimes eliminate the need to use a table lookup. So let's see how this works. So in problem 1, we have the indefinite integral of dx over 7 minus 4x. And we want to do something to make this look like the antiderivative of 1 over x dx, because that we know. So the antiderivative of 1 over x dx is natural log of x. So we're saying that looks pretty similar. We're going to have to do a few manipulations to get it to look exactly like that. So first, let's write this as 1 over 7 minus 4x with dx over here, like I did. Just pull the dx down and leave a 1 placeholder up there, and now it's even closer to what we're hoping it to look like. Now, to make this look like one term in the bottom, we're going to say, let's introduce a variable called u. In fact, this is often called u-substitution rule because we use the letter u so often in this strategy. And we're going to let the entire denominator be represented by this letter u. So therefore, I'm going to get 1 over u. And now I'm really close. So if it turns out I can get 1 over u here, and then du, that's a bad spot to write it with the blue. Well, let me not foreshadow what we're trying to do. Let's just do it, and then I'll explain why it worked. Okay, so we've replaced the denominator with this letter u, but what about dx? So it turns out that we're going to now take the derivative of u, which would be 0 minus 4, the derivative of x is dx. And now we're going to solve for dx. So the 0 is going to go away. We're going to divide by negative 4, and we're going to have dx on the right. So instead of writing dx here, we're going to write this, du over negative 4. And now we have everything in terms of u, and it looks really, really close to this form up here. So the only thing I'm going to do is put a placeholder 1 there so I can see that this is really the fraction 1 over 4, and we're going to pull that out of the antiderivative. So we get 1 over u du. And now that's exactly the same as this up here. So we're going to say this is 1 over negative 4 stays out front. Antiderivative or integral of 1 over u is natural log of the absolute value of u, and the du goes away because we performed the integral. And this is an indefinite integral, so we have to add c to this. In fact, I should have added c to this one too. Okay, now the last step is let's replace u with what it was. U is really 7 minus 4x plus the c. And that would be the antiderivative or the integral of that function. So there is no way to break that up or try anything that we learned in previous sections to do this integral. You have to use u-substitution for this one. Now this is going to seem a little strange until we do enough of these. So at the end of 10 of these, I'm hoping you'll see the pattern. There's a pattern that will emerge, and then you can do them on your own without having to see them done. Okay, so let's look at 2. And it does take a little practice to decide what you should substitute. So we have the indefinite integral of the quantity natural log of x raised to the 24 all over x times dx. Oftentimes what you're looking for is you're looking to pick a function whose derivative will equal what's left over. So in this case, if I pick u to equal natural log of x, you may recall that the derivative of this u would be 1 over x. And this x in the denominator is really 1 over x. So the derivative is accounting for that x term down there. Now we do have to write a dx here. Then we're going to solve for dx by multiplying both sides by x. So we'll get dx over here. And now we can substitute everything we know. So this is the integral of not natural log anymore. It's actually now u raised to the 24th power over x, and then times dx, but dx is really x du. So we put x du here. So notice, I should use color here, I'm replacing dx with what it is, x du. And this should always happen if you've done this correctly. You'll always get the other letter to go away. So we don't want x's anymore, and it turns out that they will cancel. X on top, x on bottom. And we get, this is the antiderivative of u to the 24th power times du. Only when I have it in terms of one letter can I now perform the integral. So everything's written as a u, so now we can do the integral. The integral of u to the 24th is just u to the 25th over 25, so that's our power rule. Add 1 to the power, divide by the same number. Because it's an indefinite integral, we have to add c to that. Then the last step is to replace u with natural log of x raised to the 25th power all over 25 plus the c. So notice how at the very last step we replace u with what it is, natural log x, which we picked at the beginning. And here's how I typed it to get it correct. So it does take a little work, because if you, let's say you picked the wrong thing. Let's say you picked u is equal to x. Well, then you'll get du is equal to dx, and you'll find that you get stuck. You can't eliminate the x letter. I see this a lot. Students want to pick everything. They'll say, oh, u is this entire thing, natural log of x raised to the 24th power. Well, the derivative of that is 24 natural log of x raised to the 23rd times the derivative of the inside, which would be 1 over x, times the derivative of x. Basically, it's getting worse. It's getting more complicated. And oftentimes that's a giveaway, is that if things are getting more complicated as you go, you probably pick the wrong thing. So these would be incorrect choices for u and then du. So again, it will take a little bit of practice to get it, but if you see enough of these, you'll start to get better at it. Okay, that's problem 2. Problem 3. Okay, so there's almost a, well, there's often a hint as to where to go. So cosine of pi over x19. Wouldn't it be nice if that was just cosine of u? Because cosine of u, I can take an antiderivative of that. It would just be sine u. So that's probably going to be the route we have to go. So again, a lot of these I will pick the absolute correct way to go. And you may say, well, how did he know to go that way? And the answer is, I've done a lot of these and practice. And the other thing is, it's okay if you pick wrong. So you might pick the wrong thing to be your u, and you'll go down a wrong path. And then you just got to start over and pick a different thing. So I know from experience that the best way to go here is let u equal pi over x19. Now that's really pi times x to the minus 19th power. Therefore, the derivative of this is bring the minus 19 down. Pi is a constant, it sticks around. Then it's x to the minus 20th. So reviewing power rule for derivative, power comes down, subtract 1 from the power, so we get this. And then a dx. Now to solve for dx, actually, let me rewrite this a little more. Du is then minus 19 pi over x to the 20th dx. So x to the minus 20 is really x to the positive 20, but in the denominator. Now to get rid of x to the 20, to solve for dx, we're going to multiply x20 over here and divide by negative 19 pi. That is dx. Okay, so let's replace what we know. So we know pi over x19 is going to get replaced with u. So this is all going to become u. And we're going to replace dx with all of that. Okay, so let's see how it's going to look. We're going to get the integral of cosine of not pi over x19, it's now u, over x20, so that's still there, times dx, but dx is x20 times du all over negative 19 pi. And again, if you've done this correctly, this will always happen. My x terms cancel and they completely go away. So the key to u substitution is you have to have only u's or constants left over. So 19 pi is a constant, that's perfectly fine. Not worried about that at all. In fact, we're going to pull out the minus 19 pi in the denominator outside of the integral, and we'll just be left with cosine u du. And the integral of cosine is sine, so this would just be sine u du. Then the last step is to replace u with what it is. It is pi over x19. So the final answer is 1 over negative 19 pi times sine of pi over x to the 19th power inside the sine function. Then there's plus a constant of integration, capital C. So let's see if I have it written the same way. So 1 over negative 19 pi sine pi over x19 plus c. Exactly the same. So that would be how you would do that one. And again, might take you a little practice to pick the right u there, but if you kind of follow along what I did, you should be just fine for this problem. Okay, problem 4. Okay, so it's also kind of a giveaway when you have lots of stuff in a square root symbol. So typically with square root symbols, we want those to just turn into the square root of u, because that we can handle. So that's what I'm going to choose u to be. I'm going to say, hey, let's let u be everything in that square root symbol, not including the square root symbol. Therefore, I can make that the square root of u and be done. Well, not done, but that's easier to integrate than what it looks like now. Now, the derivative of this would be 0, because derivative of a constant 1 is 0. Derivative of cosine is minus sine t, and then times dt. So the derivative, so I should mention that. You have to use chain rule to do this. Derivative of cosine is minus sine t, but then you have to also take the derivative of the inside, which is t, which is times dt. So it's this chain rule idea, you're doing outside to in derivatives. So du is just minus sine t dt, and you always solve for your new, for your old variable. So the old variable is dt, so let's isolate it. So divide both sides by sine t, negative sine t, and that's dt. And now I can replace that right here, and we can replace u in the square root symbol. So let's see how it's going to look. We're going to get sine t is still there. This is now the square root of u, and dt has become du over minus sine of t. And like I said, sine t on top, sine t on bottom will cancel. No more t's. There is a minus sign though, so that minus will come outside of the integral, and it's just the square root of u du. Well, this is really, square root of u is u to the 1/2 power, and the antiderivative or integral of u to the 1/2 power would be u to the 3/2 power, add 1, divide by the same number, plus some constant of integration. But let's plug in what u was. u was 1 plus cosine t raised to the 3/2 divided by 3/2 plus c. The very last step is to flip that denominator. Dividing by 3/2 is the same as multiplying by 2/3. Let's put the minus in front. Then it's going to be 1 plus cosine t raised to the 3/2 plus the constant of integration c. And that's exactly what I have right there. Okay, so that would be problem 4. All right, problem 5. This is another giveaway. So when they have a bunch of stuff being raised to a power, that stuff is probably going to be our u. So we're going to have e to the u over, and actually since they used u here, we're going to use x. So it's like x substitution instead of u substitution because they already used the letter u. So it's 3 minus e to the u du. So let's let x, our dummy variable, be 3, oops, there's a squared here, I forgot, be 3 minus e to the u. Therefore, dx would be equal to minus e to the u du. So the derivative of 3 is 0. The derivative of e to the u is e to the u, and with a minus in front, and then we pick up this du term. Therefore, solving for du, we would get dx over minus e to the u equals du. And now we can replace everything. So we're going to get e to the u is still on top. The bottom is just u squared. U. So used to using u. The bottom is x squared. Du is going to be replaced with dx over negative e to the u. And like all the previous problems, e to the u on top, e to the u on bottom will cancel. No more u's. The letter u is gone. And we're going to get this is equal to, pull this minus out front, minus integral 1 over x squared dx. That's the same as negative x to the minus 2 dx. The antiderivative of that would be x to the minus 1 over minus 1 plus c. So be careful. The antiderivative of 1 over x is the antiderivative of x to the minus 1 dx. That is the natural log of x. But if I have a power down there, if I have 1 over x squared, that gives us the antiderivative of x to the minus 2 dx. That one I can use my old school power rule. Just add 1 to the power. So adding 1 to negative 2 would be minus 1 over the same number minus 1. So you don't get natural log like we had previously. That was a special case that I showed you why that was, because when you add 1 to that power you get 0, and then you divide by 0, it doesn't work. But this one you can use the power rule. Add 1 to the power, divide by the same number. Double negative here, so you're going to get, and dividing by 1 doesn't change anything, so this is going to be x to the minus 1 plus c, which is 1 over x plus c. But what is x? X was 3 minus e to the u. So that would be the final answer here. 1 over 3 minus eu plus some constant of integration. Okay, so problem 5. Showing you these secrets here. These, well, they're kind of hints of how to go about it. Another hint. It is very, very common that you'll use u to be the highest power of your variable. So if x, the highest power, is the 9th, you probably want that to be u because the derivative of that will get you 1 power lower. The derivative would be x to the 8, which is what we have on top. So let me actually write this a little larger so you can see it better. A plus b, x to the 8, over, and there's a square root symbol here. So I also said, hey, oftentimes you're going to take everything in the square root symbol and call it u. there's kind of two hints on this one. Dx. So we're going to let u be everything in the square root symbol. 9ax plus bx to the 9th power. Then the derivative of u would be 9a dx. So that is one thing here. The derivative of x is no longer just 1. It becomes dx. Plus the derivative of x to the 9th would be bring the 9 down, leave the b alone, subtract 1 from 9 becomes to the 8th, then times the derivative of x, which is dx. And we can factor out a 9, and we can factor out a dx. So I factored the common 9 out to the left side, factored out the common dx to the right side. You're left with a, the plus sign, the b, the x to the 8th inside the parentheses. Okay, now we have everything to do the replacement. The numerator stays a plus bx to the 8th. The denominator becomes just square root of u. So we replaced all of that stuff in the square root with u times dx. Oh, we didn't solve for dx yet. Dx would equal du divided by this whole thing. 9a plus b x 8, like that. So we replace dx with du on top over 9 times the quantity a plus bx8. And surprise, surprise, let me put parentheses here. You will see this on top is exactly the same as this on the bottom. They completely cancel. Your x's all go away. And we are left with the antiderivative of, this is 1 over 9, which I can pull out front. And this would be 1 over the square root of u du. 1 over square root of u is the same as u to the minus 1/2 power du. The antiderivative of u to the minus 1/2 power would be u to the positive 1/2. So add 1 to negative 1/2, you get positive 1/2, divided by positive 1/2 plus c. This 1 over 2 in the denominator is going to flip, so you're going to get 1 over 9 times 2 over 1, which is 2 over 9, u to the 1/2 plus c. Well, this is really 2 over 9 times the square root of u plus c, but u is really 9ax plus bx9 plus the c. 2 over 9 square root 9ax plus bx9 square root plus c. So it's exactly the same. And that is how you do problem 6. So again, those giveaways are almost always in a u substitution, you're going to take everything in the square root symbol. And if you see the power of your x is 1 higher than the power of your x somewhere else, that's also a giveaway that should be your u, because when you take a derivative, it will become 1 less power, 9 becomes 8, etc. And then you're going to get things to cancel. So study that one closely. That one's kind of a nice one because it looks really messy, but if you pick your u correctly and do your derivatives, things go away and then it becomes pretty simple for problem 6. Okay, so problem 7, again, probably pretty easy to see. Take everything inside this square root symbol to be u. So we start with the integral of e to the x times the square root of 15 plus e to the x dx. So we are going to let u equal everything inside the square root symbol, not including the square root symbol. Therefore, the derivative of u is 15 goes away. Derivative of ex is ex, but then the derivative of x power is dx. Solve for dx, you'll get du over e to the x equals dx. We're going to replace that in the integral. Ex is still there. Square root of all that becomes square root of u. Dx has become du over e to the x. And just like before, ex on top cancels the x on bottom. And this one's going to look really similar to what we just did. This is the square root of u du. This is the square root of u to the 1/2 du. Integral of u to the 1/2 would be u to the 3/2 over 3/2 plus c. Last step, actually make this 3/2 in the denominator as 2/3 in the numerator. And then u is really 15 plus ex raised to the 3/2 plus that constant of integration because these are indefinite integrals. So let's see, 2/3, 15 plus ex raised to the 3/2 plus c. So that is how you do it. Last step, don't forget, replace u with what it was. We said u is this. Problem 7. Okay, problem 8, we have the integral e to the cosine of 15t times the sine of 15t dt. Now we might be tempted to let u be sine 15t because the derivative of sine is cosine, and we can get, oh, that cosine is the derivative of sine. But if you do that, you won't be able to get rid of the e part of it. The e, you'll get e to the du, which we can't do anything with. So instead, we're going to pick, so that's another common thing, is it's common to, if your exponent has some funky stuff going on, a complicated function or something, you're almost always going to pick your u to be that function. So we're going to let u be the function that is the exponent on our exponential function. So we let u equal cosine 15t. Now du would be the derivative, I'm going to actually do this one in color. Derivative of the outside would be just the derivative of cosine of 15t, which is minus sine of 15t. But then it's times the derivative of the inside, which would be 15t, which would be times 15. But then it's times the derivative of the inside, different color, orange. Then it's times the derivative of the inside of that, which is t, which would be dt. So this is truly like a chain rule done 3 times. So du is all that stuff, and so we can write it as negative 15 sine of 15t dt. Then solving for dt, we'll get it's du over minus 15 sine of 15t. And we replace everything with what we know. This is no longer e to the cosine, it's e to the u. Sine 15t is still there for now. dt we replace with du over negative 15 sine of 15t. And as we are accustomed to seeing, and this should happen every time, sine 15t on top cancels with sine 15t on bottom. T's are now gone. Let me pull out this 1 over 15, 1 over negative 15, integral e to the u du. That's one of the easiest integrals we'll ever see. The antiderivative of e to the u is e to the u, does not change, plus constant of integration. Last step, replace u with what it is. It was cosine 15t. So the final answer is 1 over negative 15 times e to the cosine 15t plus c, and you can kind of see how I typed that in. Okay, so that one, we were tempted to use sine as our u function, but I didn't take us down that dead end road. I guess I could have just to show you what it would be like, but this is what you should do to get it correct for problem 8. Okay, problem 9, we have definite integrals now. So they're giving us numbers, so we get numbers as answers, we no longer have plus c. And we have the integral from 0 to 1 of x to the 8th e minus x to the 9 dx. So there's two giveaways here. One is we almost always want to take any power on e as our u function. Well, there's double reason to do that because the derivative of x9 will become x8, which is, we already have an x8 out there. So it's kind of a double hint here. We're going to let u equal negative x to the 9th. Therefore, the derivative of u would be minus 9 x to the 8th dx. Therefore, dx would be du over minus 9x8. And we know everything to substitute in. So we're going to get 0 to 1. x8 is still there. This is now e to the u. And dx is now du over negative 9 x to the 8th. And as we suspected, x8 on top, x8 on bottom will cancel. Let's put a placeholder 1 there just so we can see the fraction come out easier. This will be 1 over negative 9, 0 to 1, e to the u du. This will be 1 over negative 9. Antiderivative e to the u is e to the u. Now there's no plus c here because I've got numbers there. And this is going to go from 0 to 1. Now you have to be really careful. This 0 and 1 is x equal to 1 and x equal to 0. But I don't have x, I have u. So we have to substitute back before I can plug those upper and lower limits into this equation. So this is e to the u, which is negative x to the 9th. And now we can plug in x equals 0 and x equal 1. I'm gonna see students make this mistake. You're gonna forget to plug back in your x, and you're just gonna plug in 1 and 0, and you will get it wrong. Okay, so now that I have x's back in there, we can plug in our limits. 1 over minus 9, this would be e to the minus 1 to the 9th, minus 1 over minus 9, e to the minus 0 to the 9th. Well, this is going to be 1 over negative 9, e to the 1 to the 9th is 1, times minus is minus 1. So be careful here. The way you have to do this is PEMDAS, powers, exponents first. So, excuse me, parentheses first, then exponents. There are no parentheses here, so exponents have to be done first. So you have to do 1 to the 9 first, then multiply by this minus sign. And it turns out in this one you'll get minus 1 no matter what, but if that was an even power, you might get that wrong. Okay, so this is e to the minus 1, double negative here, plus 1 over 9. This would be e to the 0, because 0 to any power is 0, and the minus sign on that's not going to change it. Now e to the 0, or no, any number to the power 0 is 1. So what do we get? We get 1 over negative 9 e to the minus 1 plus 1 over 9. The last thing to do is say e to the minus 1 is the same as 1 over e to the 1. So you can flip that into the denominator and make that power positive. So you get 1 over negative 9 e to the positive 1 plus 1 over 9. And I suppose you could factor out a 1 over 9th if you wanted to, but I typed it in exactly like that and got it correct for problem 9. Okay, last problem. Pretty similar. We have 0 to 1 again, e to the z plus 23 on top, e to the z plus 23z on the bottom dz. Now this one is truly kind of, you have to kind of just guess and try, but I'm going to notice that if I let u equal e to the z plus 23z, the derivative of that is the same thing, e to the z plus 23, and this is times dz. So I'm going to notice that, oh, interestingly enough, this is the exact same as that. So the derivative of e to the z is e to the z, but the derivative of 23z is 23. And then we've got the numerator matching it. So we're going to solve for dz. So du would be e to the z plus 23 equals dz. So we're going to get 0 to 1, e to the z plus 23 on top, over u. So the entire denominator is u, so we can replace that wholesale. And then dz, which is really du over e to the z plus 23. And there we have it. We love seeing this. Cancel that whole thing with this whole thing. And we're going to get, this is equal to the integral from 0 to 1 of 1 over u du. And we saw that one earlier today. The integral of 1 over u is the natural log of the absolute value of the variable u, and we're taking this from 0 to 1. But again, be careful. Don't plug in those numbers yet. This is x equal. So we have to first replace u with what it is, and it is e to the z plus 23z. Now we can plug in 0 to 1. And actually it's not x equal, it's z equal. So to know what variables we're using using z in this case as our starting variable, and then we use u as what they call a dummy variable. It's a placeholder variable just to make the work easier, and then we can substitute it back out at the end. Now we plug in 1, so we get natural log of e to the 1 plus 23 times 1 minus the natural log of e to the 0 plus 23 times 0. This is going to be natural log of e to the 1 plus 23 minus natural log of 1 plus 0. Well, this would be natural log of 1. And you can try this on your calculator. The natural log of 1 is 0. So that whole right side collapses into 0. So the final answer is just this part, natural log absolute value e to the 1 plus 23. Natural log e to the 1 plus 23. Okay, and that is a quick introduction to u-substitution method. It's going to take practice. You're going to want to see lots of these. The more you do, the better you'll get at it. And it's okay to pick the wrong thing. I didn't show you any ones that I picked wrong. Well, I kind of did earlier on, but you'll kind of know it. So if you pick wrong, you're going to hit a dead end, and then you just go back and you pick a different thing as u, and hopefully it'll work out where things cancel. And it should make your life easier, not harder. That's the whole point of this. So that would be section 5.5, substitution rule.